We are in FRQ topic 3. I like to call this rate in, rate out problems. I used to call it accumulating rates of change. Now I like to call it rate in, rate out. Kids tend to remember that a little bit better. This topic is pretty easy if we can remember one thing that comes from this statement. So we know that the integral of a rate from time A to B gives you the change in the amount on that time interval. So that gives you that change in amount. So integral of rate will always give you change in amount. So if we know that is true, then if the rate is of something entering or coming in some way, a rate in, the integral of rate in will be the amount that came in during that time interval. Rate out would be the amount that went out during that time interval. So if you can remember that, these problems tend to just fall right into place. So with that in mind, let's take a look at the problem from 2019. We have some fish in this problem. So this one was number 1 with a calculator. So I'm going to grab my calculator, clear out what's in here. Should have done that before. Okay, got my calculator ready to go here. So it says fish enter a lake at a rate modeled by function e. We have this function e. It's a complicated little function. I like to put my rate into my y1 function. So in for y1, I'm going to be putting this function. Double check, make sure you got it in there just fine. And so we're putting that in for y1. Okay, fish leave the lake at a rate modeled by function L, modeled by that. So let's put that in for y2. Make sure we got that in there correctly, and I'm going to let myself know and reinforce for you guys that we're letting that be y2. Okay. Now that we have that done, both E and L are measured in fish per hour. We'll keep that in mind. T is measured in hours since midnight. All right. Part A. How many fish enter the lake over the 5-hour period from time 0 to time 5? So the amount entering will be the integral of the rate entering, the rate in. So this is integral from 0 to 5 of our rate in, which they said was E of t. So I have that stored in for y1, remember. So math 9, 0 to 5 of my y1. So it says to round our answer to the nearest whole number. So I'm going to say that this is approximately equal to 153 fish. Don't have to say fish. They told me it was how many fish. Don't really have to say that. So that was worth 2 points. 1 point for the integral and 1 point for the answer. Part B. What is the average number of fish that leave the lake? The average number of fish that leave the lake per hour over the 5-hour period. So the average number of fish that leave the lake would be, well, first of all, we need to pull out our average value of a function. So the average value of a function would be 1 over b minus a, so 1 over 5 minus 0. So average number of fish that leave the lake per hour. So that is the average of fish that leave per hour. That is our L of t. So we're finding the average L of t. So 0 to 5, L of t. So that should give us the average number of fish that leave per hour. 1 over 5, Math 9, 0 to 5 of RY2, 6.059, and that's that question. Don't need to give units. They didn't ask for them. This was 1 point for the integral, 1 point for the answer. Okay, part C. So I will say part A, a question like part A is very typical for one of these problems. Part B, that's, this can be pretty much anything, but in this case they asked us for an average of a rate, so that's fine. Part C is another very typical question in one of these types of problems. At what time from 0 to 8 is the greatest number of fish in the lake? So greatest fish. We want the greatest amount of fish, right? So it's an absolute maximum problem, so I'm going to set up the closed interval test. We're on a closed interval, so that makes sense to me. So time is my independent variable, and we're trying to maximize the amount of fish, the fish amount. So 0 to 8 are my boundaries. Those are my boundaries. Don't have to tell AP that, but that's what they are. And also here, I need anything that makes this derivative 0, specifically 0, and since it's a greatest, we want for the derivative of this to go from positive to negative, to be a relative max. So if this is my fish amount, what will the derivative be? Well, the derivative is the rate of change, right? And the rate of change is the rate entering minus the rate leaving. So the rate entering is my E of t, the rate leaving is my L of t. So that is the derivative of the amount. Makes sense. So in my calculator, I need to tell AP what I'm doing. I want that to be 0, and I want it to change from positive to negative. At t equals, now I'm going to go find it. So in my calculator, I want E minus L. I want to see where that is going from positive to negative, so I'm going to turn off these two graphs by pressing enter on that equal to sign. And over here, I'm going to make this y1 minus y2. And then I'll put 0 down here, make it easy to find that where the graph hits the x-axis. From my window, I only need to see from 0 to 8. And I'm not sure where to put my y-min, y-max. I'm just going to maybe play around. I'm going to start with -5 to 5, and then I'll play if I need to. If it's not a great graph, I'll play with that. And I already see that this is not a great graph. I need way more on my y's. I do see where it hits the x-axis, which is great, but I want to see a little bit better here. So I think I'm going to make it look like it went way up. So I'm going to go -100 to 100, see if that helps. That's way better to me. Didn't need quite that far, but that's okay. All right. So I see something interesting. I see that E minus L is always positive until this time, and then always negative after that time on 0 to 8 hours. So this tells me, even though I started with the closed interval test, I don't need to finish with it, okay? Because the rate is always positive. That means from 0 to this time, whatever that is, from 0 to that time, the number of fish is always increasing. If the rate is positive, that means the number is increasing. And then after that time, the rate is negative, so the amount of fish is decreasing. So the amount is always increasing and then always decreasing. The absolute max has got to be at this time. Let's go find that time. So we have 5.394. Okay, so I'm going to say E minus L is greater than 0. It's positive on 0 to that time. So the amount of fish is increasing. And then I'm going to say E minus L is less than 0, negative, on 5.394, whoops, not equal to, just less than, to 8. So the amount of fish is decreasing. Therefore, the greatest number, I'm writing my answer like they gave it to me. The greatest number of fish occurs at time 5.394. Okay? So this happens a bit. This happens fairly frequently, where you start with the closed interval test, but you can't end with it. Now in this case, did we have to do it this way? Here's my answer. Did we know, plug in my computer, did we know do we know an initial value of fish? Did they give us in the problem how many fish were there at the beginning or at some other time? No, they didn't give us that at all. So we would not have been able to fill out this. Okay? I still like to write this down for myself because this guides me. It tells me, okay, I need to consider my boundaries and I need to consider a time that makes the rate change from positive to negative. So this will guide you. So go ahead and write it down anyway, even though we didn't end up finishing with it. I don't need to do anything with that. I'm just going to leave it there. It doesn't matter. Okay. Part D, is the rate of change in the number of fish in the lake increasing or decreasing when time is 5? Is the rate of change increasing or decreasing? So we want the derivative of the rate of change. If that derivative is positive, then the rate will be increasing. If that derivative is negative, then this rate will be decreasing. So we want the derivative of the rate of the amount. Well, this is the rate of the amount. So I need the derivative of that. I need the y prime at 5 minus L prime at 5. Let's see what that is. So the derivative of my y1 at time 5 minus the derivative of y2 at that time. And we get negative 10.723, which is negative. Therefore, the rate is decreasing at time 5. So I didn't say how many points this absolute max problem was. This was worth 3 points. 1 point for sets E minus L equal to 0. 1 point for the answer, 1 point for the justification. An absolute max problem is almost always worth at least 3 points. For this part D, 1 point for considers E prime of 5 and L prime of 5. And then 1 point for the answer with explanation. So that was the problem from 2019. Next up, I'd like to take a look at the problem from 2015. 2015. We've got, this was number 1 with a calculator. We have the rate at which rainwater flows into a pipe is modeled by R here. So that's my rate in, that's going to go into my Y1. Cubic feet per hour are the units. We're from 0 to 8 again. The pipe is partially blocked, allowing water to drain out the other end of the pipe at this rate. So this will be our rate out. That's going to go in for my Y2. Still cubic feet per hour, still the same time frame. Then it says there are 30 cubic feet of water at time 0. So there's an initial amount. So we can, if they ask us an absolute min or max of water in the pipe, we can go ahead and use the closed interval test if we want to. All right, so to my calculator, I'm going to put these in, change out what's here. I think I'm going to leave that Y3 in there because we tend to use that a bit on these types of problems. Let's see if I can sharpen this up again. So 20 sine of t squared divided by 35 and negative 0.04 t cubed plus 0.4 t squared plus 0.96 t. I'm going to need to give this a good look to make sure I got it correctly entered. It looks good to me. Hopefully it is. Alrighty. Part A. How many cubic feet of rainwater flow into the pipe? How much water flows in that time interval? So interval 0 to 8 of the rate in, which is our R of t. Very typical for a part A problem. So math 9, 0 to 8, Y1, 76.570. And let's see, that was worth 2 points. 1 point for the integrand, 1 point for the answer. Pretty typical. 2 points. 2 easy points. Okay, part B. Is the amount of water in the pipe increasing or decreasing at time 3? Is the amount increasing or decreasing at time 3? Well, the amount, we need the derivative of the amount, right? Well, the derivative of the amount is our rate in minus our rate out. So I want R at time 3 minus D at time 3, which is my Y1 at time 3 minus my Y2 at time 3. Not the derivatives of those, like, because in part D of 2019, they were asking, is the rate increasing or decreasing? So that's when we needed the derivative of our rate in minus rate out. This time we need just, is the amount increasing or decreasing? So the rate in minus the rate out is a negative 0.314, which is negative. Therefore, the amount is decreasing at time 3. So that was worth 2 points. 1 point for considers R of 3 and D of 3. And then 1 point for our answer with reason. Okay, part C. At what time is the amount of water in the pipe a minimum? Okay, so this is an absolute min problem, not a surprise. I have my independent variable and I want my amount to be what I'm trying to minimize. Start off with our closed interval. I also need to put anything that makes the amount, the derivative of the amount, 0, and go from negative to positive for an absolute min. So I want my R of t minus my D of t. I want that to be 0, and I want it to go from negative to positive. At t equals, so we're going to find out where that is. So back to my calculator, I still have my y1 minus y2 and the 0 in there. Kept that in there because this is a very common question for them to ask. Okay, so I'm turning off the graph for my y1 and 2 so that I only see the rate in minus the rate out. And I think I get to keep my 0 to 8. I don't know if I'll need the negative 100 to 100. We're talking about cubic feet of water. That sounds like a lot. Anyway, I'm just going to graph it and then we can always play with that. Okay, totally did not need the negative 100 to 100, right? So that's hard to see. So I'm going to come in here and we're going to lower that significantly. Let's make it negative 5 to 5. Much better. Much better. Okay, so let's see what we're dealing with here. Like last time, I see that at 0 my rate is 0, and if I look at my functions, that can be easily confirmed. When time is 0, both of those are going to be 0. So my rate is always negative until this time, and then the rate is always positive after that time. Therefore, my amount of water is always decreasing until this time, and then my amount is increasing after that time. So the amount is decreasing and then increasing. The absolute min has got to be at this time. So again, even though we started with the closed interval test, we don't have to finish with it. I need to go grab that time though. 3.272. Okay, so I'm going to say, just like we did last time, R of t minus D of t is less than or equal to 0 on 0 to that time, and since I have equal to 0, I could just say less than 0, and then I would just say less than here and less than. You just want to make sure you're saying correct things. Okay, and R of t is greater than 0 from 3.272 to 8. Therefore, the amount is a minimum at time 3.272. And they only asked for the time. They did not ask for the amount. We could have found the amount using fundamental theorem, but we didn't have to here. So I'm just going to leave it there. Now, if you want to, you can also include here, therefore, the amount is decreasing. and therefore the amount is increasing. You can say that, but it's not required to say that. This was worth 3 points. 1 point for considers. Considers R minus D is equal to 0. 1 point for our answer, and 1 point for the reason, the justification. Okay? Again, we started with closed interval test. We just didn't have to finish with it. We could have finished with it this time, though. We could have found all 3 of these amounts, and then just our reason would be closed interval test. Part D. The pipe can hold 50 cubic feet of water before overflowing. For time greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. So, this is all for time greater than 8, right? So we know that we are starting, we're starting at 30, at time 0 we have 30 cubic feet of water. At time 0 we have 30 cubic feet of water. And water's coming in and water's going out. What is the amount? Well, if we're starting at 0, then the amount coming in would be time 0 to whenever we start to overflow. W of the rate in, which is our R of t. So that would be all the water coming in over this time period, but we also need to consider the water going out over that same time period, and that will be our integral 0 to W of our d of t. So that will do it, and we just want to find out when is this equal to 50. So the amount that we start with plus the amount that came in minus the amount that went out, we need for that to be 50. So this equation will give it to us. This was worth 2 points. 1 point for the integral or integrals, and 1 point for the equation. Does the equation make sense? We could have, if we had wanted to, we could have combined these two and just make it 0 to W R minus D dt. Could have done that too. All right, and that was the one from 2015. Next up, we're going to do the problem from 2010. So let's get that out. Okay, this was, again, number 1 with a calculator. It reads, there is no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates on the driveway at this rate. So that is the amount of snow. It's always falling at this rate. So that's our amount in. So in my calculator, that's going to go in for my rate in. 7x e to the cosine of x. Make sure we got that in correctly. It looks good. Okay, so that's our rate in, cubic feet per hour. T is measured in hours since midnight. Janet starts removing snow at 6 a.m. The rate in cubic feet per hour is G of T. That's the rate she removes snow from the driveway, and it's modeled by this piecewise function. So from 0 to 6 a.m., from midnight to 6 a.m., she doesn't remove anything. From 6 to 7, her rate is 125 cubic feet per hour. And then from 7 to 9, she's slowing down, she's getting tired, so her rate is 108 cubic feet per hour. Okay. Part A. So I'm not going to put that into my calculator because it's a piecewise function, but we're going to treat it like we always have been here. Part A. How many cubic feet have accumulated on the driveway by 6 a.m.? So by 6 a.m., the amount of snow will be 0 to 6 of our rate in, that's our F of t. So to my calculator, and math 9, 0 to 6, y1, 142.275. Do we need units? Nope, we didn't. They didn't ask for units, so that's it. That was worth 2 points. 1 point for the integral, 1 point for the answer. An easy 2 points. The integral of the rate in gives you the amount in. All right. Find the rate of change of the volume of snow on the driveway at 8 a.m. The rate of change of the amount of snow at 8 a.m. So that's going to be my rate in minus my rate out. So F at 8 minus G at 8, right? Well, F of 8 I can use my calculator for. G of 8, at 8 we're at 108 cubic feet per hour. So that's what I'm going to put into my calculator. F of 8 is my y1 at 8, and I need to subtract 108 from that. Negative 59.583 cubic feet per hour. They didn't ask me for units, though. This was worth just 1 point for the answer. And answer. Okay. All right, part C. Let H represent the total amount of snow in cubic feet that Janet has removed from the driveway T hours after midnight. Express H as a piecewise function with domain 0 to 9. Okay, so H is the amount of snow Janet has removed. So I know that from 0 to 6, and I'm using the same inequality signs that they used for G. From 0 to 6, H will be 0. I know that, right? From 6 to 7, she will have removed some snow, correct? And it's going to be the amount of snow from 6 to 7, so it's going to be the integral of the rate out, correct? So the integral from 6 to 7 of the rate out, which is our G of t, and from 6 to 7 we need to use the 125 for G of t. So we're taking the integral of this. You can use your calculator for that if you want to. You know what? We need to, that would give us the total amount that she removed over this time period, correct? That would give us the total amount. We don't really want the total amount. We want to be able to find H at any time t. So we want to know not the integral from 6 to 7, but from 6 to any time. From 6 to any time. We want a function for H, not the total amount removed. Okay? So instead of making this G of t dt, let me come in and use a little bit of white out here. Instead of making it, I don't want this variable to match this variable, so I'm just going to make it an x. You could leave it a t if you wanted to, and that would be totally fine. But I'm just going to come in and do that. Okay. So we want to integrate this. It's a constant, so I know what to do with a constant in an integral, a definite integral. It's that constant times the top boundary minus the bottom boundary. Similarly, from 7 to 9, I'm going to have the integral from 7 to some time of my g function, and this time I'm using the 108 rate, so it'll be 108 times t minus 7 for that time period. So as a piecewise function, if we want to write it, h of t is 0 if the time is from 0 to 6, 125 times t minus 6 if the time is from 6 to 7, and 108 times t minus 7 if the time is from 7 to 9. And that would be our piecewise function. Points for this one. 1 point for h of t on 0 for 0 to 6, 1 point for h of t for 6 to 7, and 1 point for h of t for 7 to 9. 3 points. So that was a little bit of a different problem. They were asking us, do we know what to do with the piecewise function that they gave us for g? Okay, part D. How many cubic feet, how much snow is on the driveway at 9 a.m.? Okay, we totally know how to handle this. So how much was on, do we have an initial amount? Do we have an initial amount? Well, we know that they didn't give us an initial amount, but it says it starts to snow at midnight. So I think I'm starting at 0, right? Nothing is there at midnight. How much snow falls? The entire time, how much snow falls? That will be our integral from 0 to 9 of our rate n, our f of t. That's the total amount that fell. Now we need to subtract out what Janet shoveled away. So we need to subtract out, here comes our total amount that I thought they were asking for in part C, 6 to 7 of that g, which is 125, and then 7 to 9 of that g, which is the 108. And this will give it to us. So total amount in minus total amount out. So integral 0 to 9 of my y1 minus integral 6 to 7 of 125 minus the integral 7 to 9 of my 108. So we get 26.335. And that was worth 3 points. 1 point for the integral, 1 point for the integral, and I think they're talking about this integral, okay? 1 point for what they call h of 9, which we did find. We did find h of 9 here. They're used, maybe they, and I didn't look at the way they scored it. I looked at only their scoring guidelines here. I don't remember what they had here. I just know that this will work. And 1 point for the answer. Clearly they used the function in part C to answer this, and that's fine. All right, so that is rate in, rate out. It's easy if we remember this concept. The integral of the rate is the change in amount. If you remember that, you're in great shape for these types of problems.